Here's an example of a definite integral. We have the integral from 0 to 1 of x e to the 6x squared dx. Because we see the 6x squared in the exponent, we think that u substitution is going to work well. So I'm going to choose u to be 6x squared and take the derivative. So du is 12x dx, and dividing by 12, we get 1/12 du is equal to x dx. Okay. So now we know that the x and the dx give me the du, and we have e to the exponent here, which is u. Okay. Now, what are we going to do with the bounds? The easiest way, I think, is to change these bounds, which are x values, into bounds that are u values. Okay, so the lower bound is x equals 0. Well, u we know is 6x squared, so u is 6 times 0 squared, which is still 0. And then the upper bound is x equals 1. Well, that means that u is 6 times 1 squared, which is 6. So now my x values 0 and 1 turn into u values 0 and 6. You know what I just realized? The x dx turns into 1/12 du. I forgot this 1/12, so I'm going to stick it in front here. Okay. Now we're ready to find the antiderivative. So I have 1/12 e to the u. Fundamental theorem of calculus says I evaluate at 0 and 6. So that's 1/12 e to the 6 minus 1/12 e to the 0. We know e to the 0 is 1. So this is 1/12 e to the 6 minus 1/12. Here's your answer. You could factor out the 1/12 if you wanted to. Okay, I just want to highlight the main idea one more time. In this problem, the original problem, I have a dx. I have this function in terms of x, and the 0 and the 1 are x values. Okay, so all x stuff up there. However, once I move on to the next step, I have a du, I have a function in terms of u, and my numbers are now u numbers. So in this step, everything is about u's. Okay, it's really important that we keep the x's and u's sort of separate so we don't get them mixed up.